Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, let's do the Python version of Module 5, Linear Regression Models, Machine Learning Approach. So this is the second part. We're going to cover polynomial regression. So if you haven't watched the first part, the Python part, please make sure you go ahead and do that because I'm not going to cover the basics that we talked about in the previous one. So for example, cross-validation, etc. So we're going to just go ahead and use the code. All right, so let's go to the right folder, Machine Learning USU, go to the lectures and platforms, Module 5, Linear Regression Model. Remember, again, we covered the linear regression Python part. Let's talk about the polynomial regression. Okay, so just like the previous one, I'm going to go ahead and run it in Google Colab. Feel free to run it on your own local machine, but I'm going to do it in Google Colab. Again, this is going to be my version. Go ahead and make a copy for your own. You can play around with that copy version. So I'm going to go ahead and go back. I don't want to have multiple of them open. Okay, so let's see if there's any running sessions. Yeah, let me go ahead and erase this one. Just make sure that, okay. So I'm going to go ahead and connect. Yeah, this is the copy version, so this is good to go. So let's go ahead and connect and do our polynomial regression model. Okay, so for the polynomial regression model, the idea is that the model is still linear, right? Because the model is linear in parameters. I'm adding x2, x3, x4, to the power of 2, to the power of 3, but the model is basically linear in parameters. Let me actually show you. So here, this is what we're talking about, right? What does this x to the power of 2 do then? It helps us to come up with a nonlinear fit, right? So it helps us to make this fit more flexible. So that's what we're going to do. So, and remember, this polynomial degree is going to be our hyperparameter. So unlike the simple linear regression model that there was no hyperparameter, here we have a hyperparameter. We're going to use cross-validation to tune that hyperparameter to basically find the best model, right? The best model in the sense that the performance in the cross-validation or in the test set, not the best model that performs best in the train set. Because if you only look into the train set, the best model is always the most complex one. Let's say x to the power of 100. It's going to do a better job no matter what, right? So let's go ahead and import the relevant libraries. NumPy pandas, matplotlib, seaborn for visualization, and we are going to do from linear regression. Again, the model is exactly the same. The features are going to be different, right? So that's why we're going to work with exact same function, linear regression. This is a class. From pre-processing, we need to process the features and make them polynomial. So that's why we're going to work with polynomial features and a standard scalar. So we talked about standard scalar in our previous video. Okay, so let's ignore the warnings. For the polynomial regression, I'm going to work with a synthetic data because I want to show you the power of this model, right? Just imagine you are this powerful, omnipotent, benevolent God out there, right? And you know the exact true relationship between data, right? So you know that for a fact, there is this true relationship between x and y. Y is equal x plus 2x squared minus 3x cubed. Just ignore the noise for now. You know for a fact that there is a relationship between x and y. So ex ante, you know that the answer is d is equal to 3. If you want to use polynomial regression model, the model better be the one that d is equal to 3. This is going to be your solution. This is going to be the correct answer. But in real world, we don't see this, right? We don't observe this exact pattern in the data. The data comes with a noise. So that's what we have. So I'm going to go ahead and create this data set synthetically and then try to back out, use polynomial regression model and cross-validation, tune the hyperparameter, and see if we can get into this value 3. Okay, so that's the agenda. So just a reminder from a random module, this is my random standard normal deviation, right? Let's create 5 of them. So this is from the normal standard distribution with mean 0, standard deviation 1, 5 observations, right? And if you run it again, you get different 5 numbers. Okay, so that's my noise. I'm going to use it as a noise. So this is my x is going to be basically the 150 numbers, and then my y is going to be x plus, remember, 2x squared minus 3x cubed plus some version of the noise, right? So this is, I'm adding some noise, and don't worry why the average, for example, is 0, standard deviation is, I don't know, 2. I just wanted to make something that it has notorious behavior at the tail, so that's why I did it that way. Okay, so this is the data. Again, I know the true model. The true model is this. So let's plot this. This is a true model. So this is if I want to plot the true model, it's going to be the black here. Don't worry about the details of these codes, guys. Because we are not going to use them in our analysis for machine learning. This is a synthetic data, and I'm going to do some visualization. If you're curious, you don't understand this line of code, copy paste the entire thing in the ChatGPT, Claude, or Bard, and then ask for some guidance. So this is a true relationship out there that we're looking for, but in reality, it is not observable. Let's use this blue data and see how far we can get close to this relationship, right? Okay, so I'm gonna go ahead, again, just ignore these details. Basically, the idea is that let's go ahead and create some polynomial. Remember, our x variable is a numpy array. It's 150 observations, right? This is my x variable, simple 150 observations, random numbers. And then, for example, I can look at the first 5. So this is the first 5 observation in my x variable, okay? 1.66, 0.92, and etc. And I can go ahead and reshape it. And actually, I need to go ahead and reshape it because if I want to use that polynomial features model from scikit-learn, it works with just vector, column data, right? No. So that's why I need to reshape it to basically all the rows in one column. So now this thing is a column data, right? Column array. And yeah, now this is ready to be passed to something like this is ready to be passed to our polynomial feature class. So I'm going to say the degree is equal to 5. Let's start with 5. And then I'm going to create an object, poly. Hopefully you're seeing the pattern, right? So everything in scikit-learn is pretty much like this. You're going to create an object, and then that object is going to do something, transform the data, and etc., right? So I'm going to create this polynomial feature maker with 5 degrees, okay? So now if I apply this polynomial object to my data, so I'm going to basically do something like this, fit transform, and this is the reason that they did -1, 1, because again, this polynomial feature only work with this data like this. Okay, I think it's easier if I just not do that and show you the error. It should be super helpful. So if I remove this reshape thing and then now run the code, it's gonna give me, well, it's gonna give me some bunch of errors. Reshape your data either using array reshape. If your data has a single feature, this is our case, right? So we're going to say, I'll make it into a nice column data. Okay, so that's why we needed to add this thing. Now, so I created a data frame. We don't need to do that, but that's just for the sake of visualization, I wanted to exactly show you what's going on if you apply this polynomial feature maker to your data, right? So we apply that thing to the data. Basically, we fit transform. When you see the term fit, it means that go ahead and learn parameters. When you see transform, it means that go ahead and transform the data based on those learned parameters, right? So this is a common thing we see in scikit-learn package or in general in machine learning. So as you can see, it's going to create 5 columns and a constant. Okay, so the constant is going to be a bunch of 1s, right? Remember, linear regression, we need this thing to just basically make sure that the model has an intercept, and the rest is, this is your x to the power of 2, x to the power of 3, x to the power of 4, x to the power of 5. So as you can see, this is super simple, right? If I go ahead and change this to, where's this shape, 10, it's gonna make x to the power of 10. So I don't need to manually create that, right? So that's why we are gonna work with this polynomial feature maker kind of thing, right? Okay, so now let's go ahead and split the data. Again, this is pretty much the same as the linear regression we covered, so I'm going to speed up a little bit. So let's split the data. We're going to pass the x poly. This is a transform version of the data, and then test set 20%. Here's the head of the train set, and now we're ready to train the model, right? Look at that, exact same model, exact same stuff. So let's go ahead, fit, and then x train, y train. So why do we call it polynomial? Because now your x's are, your features are different. You have x, x to the power of 2, x to the power of 3, and etc. That's it. We created it. X, x to the power of 2, x to the power of 3, and etc. There you go. Now the model has been trained. We can look at the performance in the test and train set. So in the train sets, we are doing 75% R squared. In the test set, we are doing 53, right? So let me show you something. This is important. If I say, hey, go ahead and do 10. So what do you expect to see? You expect to see that the performance in the train set is going to be better or worse? Better. In the test set, let's see. Yeah, in the train set, we improved a little bit. In the test set, well, actually here it's increased a little bit. But as you can see, there's still a big gap. So if I go ahead and change it to 20, to 30, just make it just like crazy, then you will see that in the train set, it's going to become better and better, but in the test set, it's not. So I'm going to go back to the polynomial degree 5 to keep things manageable. We can see, observe everything. So for now, the test set 53, train set 75. Let's see if we can improve this number, right? And how do we do that? By doing cross-validation to find the optimal value for polynomial degree. Right now, we're using 5. In real world, if you were God, you know that the answer is 3. So let's see if machine learning is able to back out that number for us, that magic number. Okay, so we can go ahead. Again, this is just for visualization. We don't do things like this. I just do it one time. You can go through the code. It should be easy, straightforward. The reason that I do it this way is that because I'm going to use Seaborn package for visualization. And if I have a column like this, then I can use that column to just split the data between train tests, right? Different categories. So that's why I do it this way. But x, y, y hats, that's it. So y hats are simply the predictions, right? If I do model.predict and then pass the train set, I get y hat predictions in the train set. If I pass the test set, I get y hat predictions in the test set. That's it. So that's how we can create this. Now I have a nice table. I can go ahead and do some simple visualizations, right? Remember, the blue dots are the train set. The orange ones are the test set. And we talked about it in the theory lectures as well. Every single time. So this is the orange ones are going to be 20% of the data. The blue ones are 80% of the data. So let's see what can we look at a bunch of performance metrics as well. So we can go ahead and look at the MSE and RMSE. Again, we have done this before. Mean squared error. You have access to the errors now. Y train minus predictions. This is for the train set. This is for the test set. And obviously, MSE in the train set is better than the test set, consistent with the R square. And we can report the basically the, well, here actually is one thing I wanted to show you because we didn't cover in the linear regression. We can use some built-in metrics from scikit-learn package as well. So there are a bunch of metrics there. One of them is mean squared error. I could do this or do this. I prefer to do these kind of things manually, but really it's a matter of choice. You can go ahead and use mean squared error function from the metric module. That's super simple. You're going to say mean squared error, just pass the y and x. That's it. The y and y hat, sorry. Y and y hat. So these are the y hats. Y and y hats. Y hats are the prediction either in the train or test set. And we get exact same numbers. 94, 125. 94, 125. Okay. Now I'm going to put everything with it in one nice function. There's a reason, because I'm going to visualize the cross-validation for you. Again, I'm creating my own function. I did nothing special here. I copy-paste every single code that I had before and put it in a nice function. I call it my polynomial regression. Okay, so this is going to be the my polynomial regression. What are the inputs? Polynomial degree. Give me the x, give me the y, give me the test size. By default, I'm going to use 20%. Give me the random state. By default, I'm going to use 100. The rest of it is exactly the same that we did, right? First of all, create that polynomial features. Then create your x poly, adding the constants and etc. Then split the data. Then use the model, train the model, make some predictions in the train, make some predictions in the test, report the mean squared error in the train test and R squared, report the MSE and RMSE and R squared in the test set. And now the output of this function is give me the degrees RMSE train, RMSE test, R square train, R square test. I could report MSE as well, but it really doesn't matter. So I have a nice nice function now. I can say, use this function. What is the degree? 5. Give me the x, give me the y. That's it. It's going to generate some output for you. You used polynomial degree 5. This is, remember, this is RMSE train, RMSE test, R squared train, R squared test. So now if I go ahead and simply do it linear regression, I get this, right? So for linear regression, the performance in the train set is a lot worse, and the test set is worse. But what are we doing here? If I do polynomial 1, so basically I'm trying to come up with a simple line. So maybe that's the line. Okay, obviously it's not going to do a good job because there is this curvature in the data, but which is not captured by the linear regression model. Okay, and now I have a nice function. I can loop through different degrees of polynomial and then compare these numbers. And this is exactly what we're going to do in the next part. So I'm gonna stack these outputs in a list. So I call it output. This is empty list. I'm gonna loop through it, right? So for I in range of 1 through 8, so we want to go from polynomial degree 1 to 7, right? And then do this. Append these things. Remember, I'm not doing anything fancy here. This is my function that I created, and polynomial degree is going to iterate through 1 through 7. That's it. And append them back to back. Once you appended them, go ahead and make a data frame. The data frame is going to be all those numbers stacked on top of each other. What are the columns? The columns are these columns. Degree, RMSE train, RMSE test. So let's just label them. R squared train, R squared test. That's it. So this is going to run this. Now you know that. So this is super helpful because if the degree is 1, you look at the R squared train, R squared test. If the degree is 2, R squared train, test, and etc. Right? And then if the degree is 7, again, as you can see, the performance in the train set is getting better and better and better no matter what. This is fact. This is reality. You didn't need to do this to make that statement. It is fact. If you make the model more complex, it's going to do a better job in train set. But do we care? No. You care about the performance in the test set. So if you make the model more complex, it seems that it is getting better. Oh, it's getting worse. You see, after degree 3, the performance is getting worse. So you can either do table or simply do it in a nice plot. So I'm going to just set the index from, basically I'm resetting the index. I'm using this degree to be the index. Again, because I'm going to use Seaborn, this is just for some visualization. Now this is degree as an index. Now if I just use Seaborn and do the plot, actually here I'm using plot. So it's using the index. And then I'm going to plot R squared in the train set versus R squared in the test set. Do something like this. Okay. Now, if you look at that, so based on this thing, based on the performance in the test set, RMSE, oh, let's see. Yeah, we're dropping R squared, sorry. So we are dropping R squared train, R squared test. If I drop R squared train and test, I'm going to be left with RMSE train, RMSE test. So this is what we need, right? So that's why we have RMSEs here. So my apologies. Okay, so now I want you to just think about it. If you want to use polynomial, we use cross-validation. Well, we haven't used cross-validation yet. We are looking at the test set. By looking at the performance of the model in the test set, what is the optimal value for polynomial degree? What is your answer? 3, right? There you go. Why? Because again, we care about the performance in the test set, and it seems that if I make the model more complex, it's unnecessary. It's making the performance worse in the test set. So the answer is 3. Remember, what was the actual true model out there? 3. There you go. This is how powerful the polynomial regression models was able to capture the relationship in the data and get as close as possible to this polynomial degree 3. So isn't it beautiful? Then let's see, where are we? Yeah, there you go. But the thing is that usually we typically don't want to tune the hyperparameters of the model using the test set. Why? Because it's kind of cheating. So we talked about it. We want to make sure, even for tuning the hyperparameters of the model, we are not leaking any information from the test set. So in order to do that, what's the solution? Yes, to use cross-validation. So cross-validation is going to basically leverage on the trained data set and then generate the RMSE in the cross-validation, which is basically a best estimate for the RMSE in the test set. So in a nutshell, we want to estimate this orange curve using cross-validation, right? And see if even with that, we get to the right degrees of polynomial. So let's do that. So, well, here I think I put it just for fun, for those of you who want to become a more efficient coder, or whatever. If you care, I ask you, can you generate the same graph all in one line of code? So basically, can you make all this thing in one line of code? I think this activity used to be more fun without ChatGPT, but now if I just copy and paste the entire thing into any of these large language models, say, hey, make it more efficient, do it one line, you should get something like this. So basically, we're using list comprehension to generate that. So it's going to be exact same thing. All right. So now we are going to find the optimal polynomial degree using cross-validation. This is what should we do. Okay. Don't lose perspective here. So I wish I could do something like this, but if I only rely on the test set performance and pick the polynomial degree 3, this is cheating. I don't want to use any information from the test set. So that's why I have to use cross-validation, okay? So we did cross-validation linear regression, exact same concept here. So the model is linear regression, and then remember, d is equal to 5 so far. And then we can do, I just want to show you both cases. In the linear regression, I use mean squared error. Here I'm using negative mean squared error. So because the scoring thing is negative mean squared error, I could simply go ahead and change it to mean squared error and add a negative sign here. It really doesn't matter, okay? But I just wanted to show you both cases. So that's why let's do negative mean squared error here. Now these numbers are going to be negative numbers, obviously, because these are negative mean squared error. We can look at the average of the positive version. So this is the estimate of the MSE using the train set, but basically by leveraging train set using cross-validation, right? We can look at the RMSE, all right? So this is the RMSE when polynomial degree was equal to 5. Is everybody following? Okay, when this was equal to 5, this is, I use 5-fold cross-validation, and this is the RMSE when d was equal to 5. Now, how can I do this? How can I do something like this? Exact same concept. Put it in a for loop, right? So I'm going to put this thing, let me see, something like this in a for loop, and then create the RMSEs for different values of d, right? So let's do that. So I'm going to call it RMSE cross-validation. It's an empty list, right? I'm going to iterate from 1 to 8, including, well, not including 8, no, 1 to 7. And here's a little more involved. So why? Because for every single time, we have to create that polynomial feature thing and train a new model, right? So for example, when I is equal to 1, I'm going to say, hey, split the data. And then we are using polynomial feature degrees equal to 1. I'm doing it all in one line. Fit transform, and then that's it. This is basically x train, x test, y train, y test. Hopefully you're following. We have done this before. It shouldn't be super complicated, right? So basically this is our x features. We are passing to train test split function, and this is y, and this is test size, this is random state, okay? Now I have trained a model with polynomial degree 1. Let's go ahead and calculate the mean squared error, cross-validated version. Now let's calculate the root mean squared error and then append them all back to back. Okay. If I do it 7 times, I can make it in a nice table. Okay, 7 times. That's it, 1 through 7. And now I have access to the root mean squared error cross-validated version, not the test set, cross-validated version. That's why we needed to train every single time we needed to train a new model based on the polynomial features. Okay, so now I can plot it again. Oh, there you go. So again, even when we're using RMSE cross-validated version, we get the answer that polynomial degree should be equal to 3. Awesome, right? So this is how powerful the polynomial regression model is if the data set is well behaved, by the way, right? So for example, if you have thousands of features and then you want to pick multiple of them to be polynomial, it's going to make things complicated. So it's not worth it. And usually we do some other nonlinear regression models in machine learning. So for example, you have 10 features, right? Let me give you an example. You're predicting the price of a house and you have 10 features. And for each of those features, you want to consider polynomial to the power of 10. So 10, 10, 100 features. And then which one are you optimizing? What are you doing? It's hard to keep track of all those polynomial degrees for 10 different variables. Now, let alone if you want to do it for 100 variables, right? So we typically don't do things for if I have large number of features. We don't do polynomial regression because there are a lot more powerful models in machine learning that can capture the same nonlinearity in the data. So that's why we're going to stick to those models. Okay, but I think it's worth knowing that what is polynomial, and if you only have one feature and you want to look at different values of polynomial degree for that one feature, just like x, that's it. It's gonna do the job for you. And yeah, for PyCaret section, I'm not going to do the polynomial regression in PyCaret. Actually, I put a note here for you. PyCaret is not the best package for handling polynomial regression models. Read the documentation and tell me why. So this is your job. It's not the best, it's not the most efficient way of doing things when it comes to polynomial in PyCaret. There's a specific reason. Hopefully, if you read the documentation, you can tell me why. All right, that was pretty much it. Until the next one, take care.